But I want to talk about iterators. This was a new language feature, I think, released in Go 1.23. And there was a bit of controversy around how it was done, basically. It's a function that takes a function as an argument, and that function can be a function of multiple arities, and it returns a Boolean. We're going to demystify all of that today. I'll skip over this. Suffice to say, I've worked on a lot of languages in the past. I have a bias towards functional programming, and what I love about iterators in Go is it gives you some more of those functional programming tools. Hopefully we'll have some time at the end to look at that. And I'm an aspiring conference speaker, so there'll be a callback to this towards the end of the talk. What I want to cover today, what are iterators in general? What are iterators in Go? What do they look like? And we're going to do some real examples. We're going to implement a few ourselves, starting by re-implementing range over slice. We won't have time to re-implement range over map, unfortunately. And we're going to use that to draw out some of the patterns, the anatomy of an iterator in Go. And then towards the end, we'll have some novel examples, either a set, or we'll look at how we can build things with infinite sequences, which is something we didn't so much have support for in Go before. So an iterator, what is an iterator? I'm sure you've all seen them in other languages you've worked in, but basically it's a standard way in a language of going through, of iterating over, if you will, a sequence of values. And usually what they provide is some way of getting the next element and some way of knowing, is there another element to get, right? From a sequence or a collection type. I just skip straight to this. So hands up if you've worked with one of these languages before, Java, JavaScript, Rust, or Python. Yeah, see, that's a lot of people. So a lot of people are going to be real familiar with this. They all have an iterator concept. And the way you get a next value from your sequence, from your iterator, is very similar. It's called next in all of these cases, basically. How you know if there's another one coming, it's a little different in each cases. In particular, the Python way uses exceptions as flow control, which is very bad, of course, but never mind. You'll be overjoyed to know that in Go, it looks completely different to like all of these languages. They went in a completely different direction. So an iterator in Go is really just a special kind of function. It is a function, as I said. It takes a yield function as an argument, and that yield function can be a zero arity, that is zero argument. I don't have an example for this today, I didn't have time, but it can be one argument or two argument as well. We're going to look at those quite a lot. Those latter two are implemented as interfaces in the standard library now, this iter.seek and iter.seek2. And you'll see the square brackets there with capital letters. We have to use generics. Yay! I know a lot of people really were against generics in Golang. Alas, if you want to use iterators, you'll basically have to be in that space. The official name of this feature is called range over functions, or that's what it was called in the blog post that sort of announced it. I think in the talk, the GoConf talk that announced it too. And the idea is basically you have iter0, iter1, iter2 are one of these functions that we just looked at. Oh, I just noticed a typo, that should be iter2. And you'll range over it, right? Iter1 will give you a 1 value for range. Iter2 will give you a 2 value for range. So you can imagine this is like the range over a slice where you're looking at the indices. This is range over slice where you're looking at index and value, or key and value range over map, right? So this function that we pass into our iterator function is called yield by convention. And as we said, this accepts 0, 1, or 2 values. Those values get assigned to these loop variables. So when I call yield with k or k and a v, that k or kv get assigned to these loop variables here. The yield function returns a Boolean, and the Boolean tells you, should your iterator function give me another value? Do I need a new value, if you have one available, right? So if it's true, keep going. If it's false, you should bail out and stop iterating. So we're going to re-implement the single index range over slice to see how this would work. So the way to think about this exercise is, this is going to be quite tricky with one hand, but there we go. Imagine range over slice were not implemented in Golang language, right? And Go gave you this iterator and you had to implement it yourself. How would we do that? Yeah, this is going to be really tricky. I'll have to put this down while I do it. We can try that. I don't know how well that will go. Can everyone hear me all right if I just speak loudly? Yeah. Perfect. So we're going to write a function called one_argument_slice_iterator. And that's going to be the iterator that iterates over a slice, iterates over the indices of that slice. The values in these collections are from the Expanse book series, which I was reading when I wrote this talk, so don't pay too much attention to the actual contents. So this should return our iterator. So that's going to be an iter.seek. And, well, the dreaded generics. This has to be a generic because iter.seek is generic. So we need a type parameter t. What should we return from this? It has to be one of those iterator functions. So generally, it's going to be we return an anonymous function that takes the yield function with one value. So I'll call that e, because I'm going to use I in a minute. That's going to be of type t. And it is, so this should be actually an int. Yeah. Why should that be an int? That should be an int because we're iterating over the indices. That's what we're going to have in the loop. So shouldn't be a t yet. We'll get to that later. And this, so how should this function look? So what do we need here? We need some way to keep track of where we are in this slice, which index we're at. So I'm going to call that I. It's a classic. Everyone loves it. Uncontroversial. And we're going to need a for loop. Why? Because we need to go over through that slice somehow, right? So we're going to take a for. We have a natural exit condition, right? So we can't keep iterating if we've gone off the end of the array. So I need to take, of course, the slice here. So I'm iterating over this slice. C, I've called it C for collection. Call it what you want, I guess. If that's less than I, that means we've gone off the end of the slice, and we can't keep iterating, so we're just going to bail out. Then what should we do? We have to call the yield function. So this yield is saying, I give you a value to use in the for range loop, basically. So we're going to yield the index I, and that yield is going to return this Boolean. So this Boolean, I'll call in this talk another value, because it's the answer to the question, should I give another value? So if I shouldn't give another value, I should bail out. And I kept forgetting this during practicing. You have to increment the I. Otherwise, you'll be stuck forever, right? Oops. Hit the wrong button there. There we go. So I think I uncommented this in main.go. So if I now rebuild and run this, we should see, what do we have? 0, 1, 2, 3, which are the 4 indices of the elements in this slice. It's pretty unimpressive, right? But that's a custom iterator, right? We've re-implemented range over a slice in Go, right? And that doing that has given us an insight into the key things that we will probably need in any iterator. So any iterator that we write in Go is probably going to have these things. It's definitely going to have a call to yield, because yield is how we return the value back to the for range. So that's non-negotiable. If we're working with a finite collection or a finite sequence, we're going to have some way of keeping track of where we are in that collection. So some sort of loop counter like I, some sort of natural exit condition like checking where we are in the slice or where we are in the data structure. We're going to have that, which we're going to have to increment, of course. And if we're going to be a good citizen, we should return when we see that this another value is false. So I think if you don't do this, you will keep iterating even though you shouldn't. So this is essentially non-negotiable as well. And just bear in mind, if you're doing something non-trivial, like, I don't know, opening a file, opening HTTP connections, database things, this is where you might do your cleanup, right? You might also do it in a defer, depends upon the situation, but that's something to keep in mind. So that just summarizes what we already said. So I think one of the things that was, I didn't immediately wrap my head around with these iterators is which functions are we working in the context of throughout all of these stages. So I want to talk us through like an illustrative sequence of operations in my example here, and how the call stack looks. It's not the real call stack. I think either the compiler or the runtime does some clever stuff, so you wouldn't actually see this call stack, for example, if you panicked during the for range, but I do think it's illustrative. So the first thing that happens is we call our function which constructs the iterator, and this only happens once, right? So we call the function, it returns this anonymous function, and that's it. We never go back into the one argument slice iterator function. After this, we'll only ever be in the anonymous function. The for range will essentially call the anonymous function. So now we're in this range over slice, one arity main, and we're inside the anonymous iterator function. So we're about here when we start off, right? We're doing this setup until we make a call in that function to yield. So at that point, the iterator calls yield, and the first time, of course, it will do that with a value 0. And you can imagine this is the imaginary call stack. We're still inside the context of that anonymous iterator function, but we're now also inside the context of that yield function, right? What happens then? The I in the for range gets assigned a value of 0, and the for body executes. So now we're inside this yield, and we're executing the for range body. Then once we get to the end there, so once the for loop is completed, yield returns, sort of. It returns that Boolean, right? So you'll get the Boolean assigned to another value here, and you're back in the context of the iterator. So you continue down this path, back to the start, then so on and so on forever, right? Next thing we do is we return 1, we provide 1 to yield, and that gets assigned to the I in the for range, et cetera, ad nauseum, as I've said here. Okay, there's a stray piece of text there, but never mind. If you have questions, I'm going to make time for them at the end, because I appreciate this may be a little interesting. But we're going to repeat the same thing again, but with the 2-value range over slice. So we're going to see how we would do an iter.seek2, or a 2-argument iterator function. And to be honest, it's basically the same as the first one. It is not much more complex. In fact, to save a little bit of time, I might just copy-paste this to start with and just highlight the differences. So we're going to want this one called 2-argument slice iterator. So how would we do this one? We would, it's still over t_any, right? Because we can have any type of element in the slice. But now, this is going to be an iter.seek2, and it will return integer and t. So that's the index is an integer, and the t is the value, the type of the value we're going to return. And to adapt this, the only thing we need to change is we return, we need to change this one as well. So this is now a function that takes the index and the value, I call it v, which is of type t. Right, so now our yield function has to accept the integer index and a value of type t. So we need to change the signature of the anonymous function that we return. So yeah, those are the only changes we need to make. Change the seek to seek2, change this to match the shape of seek2, and provide the extra argument to the yield function. And so did I uncomment that here? Yes, I did. I'll comment out that one so we don't get extra stuff. And there we go. So we've here printed, well, if you want to check that I'm not lying, that's the contents of the slice. And you'll see here we've print lined the index and the value in the slice. So there we go. We've re-implemented both the one value range over slice and the two value range over slice and go using iterators. And it was pretty easy, right? Not too hard at all. Yeah, I'm going to skip over this example because I think there's some more interesting stuff a bit later. But I would just say that using a very similar technique, you can re-implement range over map using iter.seek2, if I'm saying it correctly. The only wrinkle is that it's a bit hard to get the keys out of a map without using another for range, right? There is a way, there's a hacky way to do it, but it only works on like specific types of keys. So I've implemented it here for a map with string keys. There's this reflect.valueOf that you can use to get a list of, get a slice of strings which correspond to the map keys. If you want to look at this, I'll give the GitHub link at the end of the talk. The example is there somewhere. Okay, so there's two more interesting examples that I have. Now we've gone over the basics and understood the anatomy, what we need in these iterators. I'm going to see how much I can get through. So in the first one, the first example is a set concept. So if I said a set in computer science or programming languages, how many people here would know what that means? Okay, about half. So basically a set is, think of it as a collection of elements with no duplicates. It's usually unordered. It's not always unordered. It doesn't have to be. And we're going to explore that example as a way of understanding the difference between eager computation and lazy computation. So actually, if I said eager computation and lazy computation, how many people here would understand the difference between those two? Okay, we're at about half as well. Oh, that's cool. So, well, I have to explain it for our friends here who maybe haven't heard of it before. But a rough way to understand it is when we eagerly evaluate something, like a collection of entities, it essentially means we do all of the calculation and the work and the transformation stuff up front. So we do all the calculation, we put it in a collection, and then we do what we need to do with that collection. Lazy evaluation means we defer calculation of things until the point at which we need them, right? So if we imagine that let's say we're working on a slice of elements and we're mapping them, we're making a change to them. With an eager evaluation, we would go through the whole slice, do all the calculations, and then use that slice. With lazy evaluation, as we pull, let's say, elements from the collection and use them, the transformations and the calculations that we do on them happen at the point at which we use them. Hopefully that will become a bit clearer when we talk about this set example. So, like I said, set is a collection of elements that contains no duplicates. It's usually unordered. It's going to be unordered in this case because it's easier to implement. And I'm going to look at how we can do that in an eager way first, in a lazy way second, and I'm going to illustrate why you might care, basically, why you might care if you do this in an eager or a lazy way. So let me switch over to my sets file. I've got some stuff set up there already. So we're going to start with a small slice. You can see this has all of the numbers from 1 to 10. It's supposed to have a 0, so I'm going to add some zeros. And there are duplicates in there, right? So we're going to want to get a set of elements which are not duplicates. So I'm going to, the way that I set myself up to implement this, which maybe was more complex than it had to be, is through a struct. So we're going to call it, sorry, that should be type set. And that should be generic over t comparable. This needs to be over comparable because we need a notion of equality. We can't eliminate duplicates if we don't know what's equal. So that's going to be a set of elements in that set, which are non-duplicates, slice of type t. So we are going to create that with a new set function. Hope I'm doing this right. So we're going to take a collection in there. And we're going to return the set out of it. Return set, and we're going to create a slice ease to gather those elements in a second. Now, how do we do this? What would be the natural tool to reach for in Go if you wanted to get a set of things which are not duplicates? Someone's got their hand up. Map, yes. So we would generally do this with a map, right? So we would do some map is, it's going to be a map of t to empty struct. I'm sure everyone knows that trick. And we don't need a size because that's a map. Then what we do, I'm going to assume for speed that we have for range over slice here, otherwise we're going to have to re-implement it, it's going to be a mess. So we're going to get all of the values from that C slice, that collection, and we're going to put them into this map. Oops, equals struct. And then what we want to do is get, sorry, that should be over C, it should be range C, that's why it's unhappy. And that should be V. Ooh, all these mistakes. There we go. Perfect. Easy to fix, though. Right, so we've got them all as keys. There is now a function in the standard library that lets you get all the keys really easily, but I'm not sure if there's a way to do that before generics. So one way we can do this is we can, I'm going to do this in a way that's reasonably performant, because so as not to bias my little comparison I'm going to do later. And then we're going to do this, and we're going to so we're going to get the values from the map. So we're going to iterate over the map here, get the values, and we're going to put the value in the elements. ESI equals V. And we're going to increment I. Does that make sense? No, sorry, it has to be the keys, doesn't it? Because the values are those empty structs. So we can actually get rid of that. Yeah. Yeah, there we go. And I think the last thing we need is the type here. So now we've created our set, and that ease should contain no duplicates, right? We're doing this eagerly. What do I mean there? When we create the set, we do the calculation. We do the whole calculation at that point. That's why it's eager. And I'm just going to implement then the elements function that we're going to need for the example to work. That should be here. That returns a slice of type T. And I need to name that. So I have s.es. So hopefully, unless I've messed something up in the rush to meet my time. There we go, perfect. So now basically I've run this code at the top here, some small slice, created the set from it, and eagerly, and printed out the elements. You'll see we get 0 through to 10. They're not in any order. There are no duplicates, right? So now how can we use iterators to do this in a lazy way? So I've teed myself up here to create this with a function called lazySetIterator. That's also T comparable, and that's going to work. That's going to take a collection and return, of course, an iterator over type T. So now we essentially need to do this one at a time, right? So we'll take the elements that we used before. So it's a func, an iterator func, which is a func, taking the yield as the argument with func, I'll say k here. I don't remember which variables I'm going to use in the body. And so we essentially need to do the same thing as we did before, right? We need a map to keep track of which ones we've returned before. It should be a map of type T to empty struct. And then we can start our for. Yep, we need to keep track of where we are in that slice as well, right? We have a natural exit condition when we've run off the end of this slice C. So if we've run off the end of that, we should return. We can't iterate any further. So the next thing we need to know is, have we seen the element at index I in slice C before? The way we do that is we just check if it's in the map. So we're going to have MCI. And if we have seen that before, if it is in the map, we're just going to continue. Now, there's something I kept forgetting, and you have to trust me that this makes things easier. I start I at -1 and I increment it at the start of the loop. Otherwise, we'll have a bad time if we forget that. So we're going to continue, right? We're going to look at the next element in the slice. We've seen it before. We don't want to return it. We don't want to yield it. If we haven't seen it before, sorry, we want to put that element into the map as a key, so we won't return it again, and then we can yield. So we're going to yield MCI. I appreciate we could probably make this a bit tidier with, that should just be CI, sorry. We could probably make this a little tidier with some sort of variable if we stored MCI in a variable. But I think it's better for the purposes of the demo if we don't do that, sorry. If not, another value like this. So I think that's correct. If it's not correct, I have a fallback code that we can go to make sure it does work. But what we should see, so what are we expecting to see? We're expecting to see 0 to 10 printed. It might not be in the same order, and it should say lazy before it, basically. Yeah, and it worked. Oh, thank God. No. So we've got 0 through 10 printed once each. Actually, you'll notice in this case they're in the same order as the first time it sees them in the slice, which is a consequence of how we've implemented. You know, a set generally doesn't give you any guarantees. This is the same as we had before, basically, right? So why should I care? So let's see what happens now if I do this on a big slice. And by big slice, I mean 10 million elements, right? So maybe we're working with some big data. I think we're going to have to run this a couple of times to see what happens. So we make the slice, which takes quite a while. And then we're going to iterate over using the eager approach. So we've started ranging over the eager. And what you'll see is because we're constructing that set eagerly, there's a long latency before we get the first value in that slice, right? So I'll just run that again in case we didn't see it. Making big slice. It's the problem with demos with lots of stuff in them. There's a lot of waiting around. So yeah, so nothing happens, then everything will happen at once. But what happened, it's easy to miss as well because it will be easier to see if I make this a bit taller. But you'll see when we do the start ranging over the lazy case, the time to first element is almost instantaneous. It's very quick. So this is the eager one. We're building the set, then everything, right? There was no gap between start ranging and the time we first got the element. All of the wait is at the end because we're going through everything and seeing we don't want to return that again, that's a duplicate. So this may be useful if you have a latency sensitive situation, for example. That's one reason you might care about iterators. I would love to talk about infinite sequences, functional programming, and all of these things that I love, but we don't have time today. I will just pause on this slide because I promised someone that I would. Using some things that iterators give us, we can start to construct pipelines of data in the way that we might do in functional languages. So here you'll see in Elixir, we can construct something in Go that looks almost identical. It's a very natural way to think functionally. And then the same in Clojure, right? This looks very similar to how it would look in Clojure. And as a functional programming advocate, that excites me a lot. You may hate it. Come discuss it with me after the talk. Happy for positive and negative opinions. But thanks very much. Thanks for listening. I also want to say thanks to the organizers for having me and letting me give this talk. I'd love to hear, your brutally honest criticism, feedback, and I'm considering to make this try and make this a GopherCon talk, flesh it out, more demos, full hour. Come tell me if you think it would be good or not. The links are at the bottom if you want to look at them. Thank you very much. I didn't quite get 27 minutes, I think it was 29, so yeah. Apologies.
Thank you so much, Scott. We do have a couple of minutes for questions if you want.
Yeah, I definitely want.
Yeah.
You've got a nice blog post on this because that was really fast.
I haven't, but I'm happy to write that blog post if you think it's valuable.
Please do.
Okay, that's on my to-do list.
You can take another question.
What do you think the benefit of... is there a performance hit by using an iterator over something else? Interesting. So that's I don't know is the honest answer, because I don't know how much trickery the compiler and the runtime's doing to get rid of the overhead of like, as we saw in the iterator, you're like calling a function and you're moving between functions, and that usually implies that you're doing stuff on the stack, and there's usually overhead there. But if you, like I said, if you panic inside that iterator, you don't see those function calls. So I don't know if the compiler or the runtime's doing something clever to remove that overhead. I'm just not sure.
It is slow.
Oh, you've measured it.
Yeah, it's quite slow.
Oh, interesting. Cool. Do you have a blog post about that?
GopherCon, a few years ago, Brian Warren mentioned it because he was experimenting with it.
Right.
So,
Okay. Yeah, I mean, who knows, like, if they've done performance optimizations in the meantime.
of the language, but
Yeah.
it's slower.
Yeah. Cool. So yeah, well, maybe, as always, if you have performance limitations, do your measurements before you use any of these tools.
Okay, thank you so much. Now let's thank Scott for his talk once again.
Thanks very much. Thanks for listening.